March 15, 1943, RAF Big Hill, England. Flight Sergeant Tommy Mitchell watches another Spitfire limp back to base. Fuel gauges reading empty, vapor trails of precious avgas streaming from bullet holes in the wing tanks. The pilot, Squadron Leader James Hartwell, climbs out of his cockpit, shaking his head in frustration. 20 minutes into the escort mission over the channel, he'd been forced to abort and return home. Not because of mechanical failure, not because of enemy action, because his Merlin engine was drinking fuel like a man dying of thirst. This scene repeats itself across fighter command airfields throughout Britain. Spitfires and Hurricanes, the legendary defenders of the realm, are prisoners of their own fuel consumption. While German Messerschmitt 109s dance through the sky with seemingly unlimited endurance, British fighters operate on a razor's edge of range limitations. Escort missions deep into occupied Europe remain pipe dreams. Bomber formations venture unprotected beyond the 180-mile radius where British fighters must turn back or fall from the sky with empty tanks. The numbers tell a devastating story. A Spitfire Mark 9 burns 94 gallons per hour at military power. With internal fuel capacity of just 85 gallons, combat operations last barely 45 minutes before pilots must choose between continuing the fight and making it home alive. Squadron commanders brief their pilots with grim mathematics. Takeoff and climb consume 15 gallons. Transit to the combat zone burns another 25. That leaves 45 gallons for combat and return, assuming perfect conditions and flawless fuel management. But combat is never perfect. Dogfights at full throttle drain tanks in minutes. Emergency power settings consume fuel at twice the normal rate. A single extended engagement can leave pilots with insufficient reserves to reach friendly territory. The statistics are brutal. Fighter Command loses more aircraft to fuel starvation than enemy action in the first quarter of 1943. Experienced pilots bail out over the English Channel, watching their undamaged fighters crash into the waves because mathematics defeated what German guns could not. What makes this crisis particularly maddening is that everyone knows the solution exists. Deep in the engineering departments at Rolls-Royce and the Ministry of Aircraft Production, brilliant minds understand exactly how to extend fighter range. Advanced fuel injection systems, sophisticated mixture controls, high-pressure carburetors that automatically optimize fuel consumption throughout the flight envelope. The technology exists, the problem is implementation. Retrofitting thousands of operational fighters would require months of factory time, specialized tooling, and engineering resources that simply don't exist in wartime Britain. Air Chief Marshal Hugh Dowding addresses squadron commanders at a classified briefing on March 18, 1943. His words carry the weight of strategic desperation. Gentlemen, we face an impossible equation. Our fighters possess superior speed and maneuverability to anything the Luftwaffe fields. Our pilots demonstrate skill and courage that history will remember. But we cannot fight where our fuel cannot reach. The Americans are producing bombers faster than we can escort them. Without extended range capability, daylight precision bombing becomes suicide for our allies and strategic failure for the alliance. The assembled officers understand the implications perfectly. Britain's entire strategic doctrine depends on daylight bombing campaigns that require fighter escort deep into German territory. Without that escort, bomber losses become unsustainable. Without bombers, the Western Front remains a stalemate while Soviet forces bear the brunt of German military might. The war's outcome hinges on fuel consumption rates in British fighter engines. Technical solutions exist in theory. Fuel injection systems eliminate the carburetor problems that plague negative G maneuvers while providing precise mixture control for optimal efficiency. But fuel injection requires complete engine modifications, specialized manufacturing, and testing protocols that consume precious time. Advanced carburetor designs with automatic mixture controls promise significant improvements, but again demand factory modifications that take aircraft out of service for weeks. Meanwhile, German fighters operate with apparent impunity over their own territory. Messerschmitt 109s with fuel injection systems perform unlimited negative G maneuvers while maintaining optimal fuel consumption. Their pilots exploit British fuel limitations ruthlessly, forcing extended dogfights that drain Spitfire tanks before disengaging to safety. Luftwaffe tactical doctrine specifically targets British fuel constraints, drawing fighters into fuel-consuming pursuits that end with British pilots nursing empty tanks across the Channel, while German aircraft land comfortably on nearby airfields. But 200 miles southeast of London, in a cramped maintenance hangar at RAF Hornchurch, a 28-year-old corporal is sketching modifications in a grease-stained notebook that will prove every expert wrong. His name is Corporal William Billy Davies, and his unauthorized experiment is about to revolutionize fighter warfare. Davies doesn't possess engineering credentials. He never attended university, never studied aerodynamics or thermodynamics, or any of the sophisticated sciences that govern aircraft performance. What he does understand, with the intuitive clarity that comes from years of hands-on experience, is how Merlin engines actually behave under operational conditions. He's maintained over 200 Spitfires since 1940. He's cleaned countless spark plugs fouled by rich mixture operation. He's calculated fuel consumption rates for hundreds of combat missions. Most importantly, he's noticed something that escaped the attention of every qualified engineer in the Royal Air Force. The Merlin engine's factory carburetor settings optimize for maximum power output, not maximum efficiency. This makes perfect sense for combat operations where raw horsepower determines survival. But those same settings waste enormous quantities of fuel during the transit phases that comprise 80% of most fighter missions. Davies has observed that pilots operate at military power throughout entire missions, even during cruise phases where reduced power would provide identical performance with dramatically lower fuel consumption. The insight that changes everything comes during routine maintenance on Squadron Leader Hartwell's Spitfire on March 20, 1943. Davies notices unusual wear patterns on the carburetor's mixture control mechanism. The enrichment jet shows excessive carbon buildup, indicating consistently rich operation. The lean mixture jets remain virtually unused, their passages clean and unobstructed. In that moment, Davies realizes that British fighter pilots are essentially flying with the fuel equivalent of a stuck accelerator pedal. Factory mixture settings provide the rich fuel-air ratios necessary for maximum combat power. But during cruise flight, when maximum power isn't required, those rich mixtures waste fuel without providing corresponding performance benefits. German fuel injection systems automatically lean the mixture during cruise operations, optimizing fuel consumption for flight conditions. British carburetors lack this capability, defaulting to rich mixtures regardless of power requirements. Davies runs preliminary calculations in his notebook using consumption data from recent missions. A Spitfire operating at optimal cruise mixture could extend range by approximately 40% while maintaining identical performance characteristics. The modification requires no exotic materials, no factory modifications, no engineering approvals that take months to obtain. Everything necessary exists in the standard carburetor assembly, waiting for someone with the knowledge and courage to make it work. The solution appears deceptively simple. Modify the carburetor's automatic mixture control to provide proper fuel-air ratios across the entire power spectrum instead of defaulting to rich mixtures. Create multiple mixture settings that pilots can select based on operational requirements. Rich mixtures for combat, lean mixtures for cruise, with automatic controls that prevent engine damage from improper selection. But simple solutions often hide complex implementation challenges. Carburetor modifications require precise calibration to prevent engine failure. Too lean and engines suffer detonation damage. Too rich and fuel consumption remains problematic while spark plugs foul rapidly. The balance between efficiency and reliability demands expertise that Davies supposedly lacks. What Davies does possess is 3 years of maintaining combat aircraft under impossible conditions with inadequate resources. He understands British fighter engines better than the engineers who designed them because he's repaired every possible failure mode under combat stress. That practical knowledge is about to prove more valuable than all the theoretical expertise in the Ministry of Aircraft Production. Davies doesn't ask permission. He knows exactly what would happen if he filed a formal modification request through proper channels. Squadron Armament Officer to Group Engineering to Fighter Command Headquarters to Ministry of Aircraft Production. Committees would review it. Engineers would demand stress analysis, endurance testing, formal approval protocols. By the time anyone made a decision, the war would be over and half the Royal Air Force would be resting on the bottom of the English Channel. So on the night of March 21st, 1943, after the flight line shuts down and the last patrol returns, Davies and 2 trusted mechanics, Corporal Eddie Walsh and leading aircraftman Peter Knox, wheel Squadron Leader Hartwell's Spitfire into the maintenance hangar. The aircraft they've chosen isn't random. Hartwell's machine has the worst fuel consumption record in the squadron, burning through its entire load in 38 minutes of mixed operations. If Davies can fix this particular fuel hog, he can fix anything. The modification itself requires surgical precision with crude tools. Davies removes the carburetor's automatic mixture control unit, a complex assembly of springs, diaphragms and metering jets that governs fuel flow throughout the engine's operating range. Factory settings provide rich mixtures across the board, optimizing for maximum power at the expense of efficiency. What Davies needs is variable mixture control that automatically adjusts fuel delivery based on throttle position and manifold pressure. Working by flashlight to avoid attracting attention, Davies begins reshaping the mixture control's metering characteristics. Using needle files salvaged from crashed aircraft and calipers borrowed from the machine shop, he modifies the fuel metering jets to provide leaner mixtures at cruise power settings. The primary jet remains unchanged for combat operations, but secondary and tertiary jets receive careful attention to optimize fuel flow at reduced power settings. The critical innovation comes from Davies' understanding of pilot behavior under combat stress. Asking pilots to manually manage mixture controls during high-stress operations guarantees mistakes that kill engines or worse, kill pilots. Instead, Davies creates an automatic system that responds to throttle position. At full throttle, the carburetor provides rich mixtures for maximum combat power. At cruise throttle settings, it automatically leans the mixture for optimal efficiency. The transition happens seamlessly without pilot intervention. But the real breakthrough lies in Davies' solution to the altitude compensation problem that has plagued British fighter operations since 1940. As aircraft climb to combat altitude, decreasing air density affects carburetor performance, typically requiring manual mixture adjustments to prevent engine roughness or power loss. Davies modifies the carburetor's altitude compensation system using components salvaged from damaged navigation instruments. Aneroid bellows from wrecked altimeters provide automatic pressure sensing that adjusts fuel metering based on altitude changes. The work consumes 3 nights of clandestine effort. Davies and his conspirators operate in complete secrecy, knowing that discovery means court-martial for unauthorized modification of military equipment. They fabricate custom tools from scrap metal, calibrate fuel flows using makeshift test equipment, and perform precision machining work that would challenge professional engine shops. Everything must be perfect because there won't be a second chance. Testing begins at dawn on March 24th, with Squadron Leader Hartwell completely unaware that his aircraft has been transformed. Davies briefs him on new fuel management procedures disguised as routine operational updates. Use cruise power for transit phases. Reserve military power for combat engagement. Monitor fuel consumption closely and report any anomalies immediately. Hartwell nods absently, assuming this represents standard efficiency directives from group headquarters. The first test flight exceeds every expectation. Hartwell's Spitfire climbs to 25,000 feet, cruises for 90 minutes at optimal efficiency settings, performs aggressive combat maneuvers for 15 minutes at full military power, and returns to base with 23 gallons remaining in the tanks. Under factory carburetor settings, the same flight profile would have left him gliding home on fumes with barely enough fuel to reach the circuit. More importantly, engine performance remains flawless throughout the flight envelope. Throttle response matches factory specifications. Maximum power output shows no degradation. The engine runs smoother at cruise settings, indicating improved combustion efficiency from proper fuel-air ratios. Davies watches from the flight line as Hartwell shuts down, counts the minutes while the pilot completes his post-flight inspection, holds his breath as the fuel truck arrives to measure remaining capacity. When the numbers come back, Davies allows himself a moment of quiet satisfaction. Fuel consumption has dropped from 94 gallons per hour to 61 gallons per hour at cruise power settings, while maintaining identical speed and altitude performance. Combat power consumption remains unchanged at 94 gallons per hour, preserving full military capability when needed. The modification has extended operational range by 67% without compromising combat effectiveness in any measurable way. But Davies' moment of triumph lasts exactly 20 minutes. At 1400 hours, during routine post-flight inspection, Chief Technical Officer Flight Lieutenant Robert Pierce discovers the unauthorized modifications. Pierce immediately summons Davies to the squadron office, where the conversation begins with military precision and deteriorates rapidly into barely controlled fury. "Corporal Davies," Pierce says, his voice carrying the clipped authority of a career officer who has never doubted the importance of proper procedures. "Would you care to explain the unauthorized equipment modifications discovered in Squadron Leader Hartwell's aircraft?" Davies stands at rigid attention, knowing his military career hangs in the balance. "Sir, I implemented fuel efficiency improvements to extend operational range." "You implemented what?" Pierce's voice rises dangerously. "Do you have any comprehension of the regulations you violated?" Technical Manual AM1B explicitly prohibits unauthorized modifications to engine systems. "This isn't your personal workshop, Corporal. This is His Majesty's Royal Air Force, operating under wartime conditions where unauthorized modifications can compromise aircraft safety, mission effectiveness, and pilot survival." The lecture continues for 10 minutes, covering everything from chain of command to proper modification procedures to the court-martial possibilities facing enlisted men who think they understand engineering better than qualified professionals. Pierce's fury is genuine and justified according to every regulation in the RAF manual. Davies has violated direct orders, modified critical aircraft systems without authorization, and potentially endangered pilots through untested modifications. But Squadron Leader Hartwell chooses that moment to enter the office, still wearing his flight suit and carrying his helmet. The conversation he interrupts will determine whether Davies faces court-martial or recognition, whether his modification spreads throughout fighter command or dies in a disciplinary hearing. "Sir," Hartwell says, addressing Pierce with the casual authority of a combat veteran, "I need to discuss my fuel consumption figures from today's flight." Pierce looks up from the disciplinary paperwork he's been preparing. "What about your fuel consumption, Squadron Leader?" Hartwell glances at Davies, then back at Pierce. "Sir, I just completed a 2-hour flight that should have been impossible with standard fuel loads. Whatever Corporal Davies did to my carburetor, it works. I had 23 gallons remaining when I should have been running on fumes." The room falls silent except for the distant sound of Merlin engines warming up for afternoon patrols. Pierce stares at the fuel consumption report, then at Davies, then back at Hartwell. "Squadron Leader, you're saying this unauthorized modification actually improved aircraft performance?" "Not just improved it, sir. Transformed it. I could escort bombers to Berlin and back with fuel to spare. This changes everything we thought we knew about operational limitations." Pierce sets down his pen slowly, the court-martial paperwork temporarily forgotten. The implications are staggering. If Davies has actually solved Fighter Command's range crisis using nothing more than carburetor modifications, the strategic possibilities become limitless. Long-range escort missions, deep penetration sweeps over occupied Europe. The kind of operations that could fundamentally alter the air war's trajectory. But regulations exist for reasons that transcend individual success stories. Pierce has witnessed too many unauthorized modifications that seemed promising in initial tests, but failed catastrophically under extended operations. Engine modifications require exhaustive testing, statistical validation, engineering approval processes that exist to prevent disasters that kill pilots and lose wars. Pierce walks to the window overlooking the flight line, watching mechanics service aircraft for the next patrol. The weight of command decisions bears heavily on officers who must balance innovation against safety, individual initiative against military discipline. Finally, he turns back to Davies with the measured tone of a man making choices that could save or doom hundreds of pilots. "Corporal Davies," Pierce says slowly, "you've placed me in an impossible position. Your modification violates every protocol designed to prevent catastrophic failures. But if Squadron Leader Hartwell's report is accurate, you may have solved our most critical operational limitation." He pauses, studying Davies with new attention. "How certain are you that this modification won't cause engine failure under combat stress?" Davies meets his eyes steadily. "Sir, I've tested every component under simulated combat conditions. The mixture control responds properly throughout the power spectrum. Engine temperatures remain within normal parameters. The automatic altitude compensation prevents the lean mixture problems that cause detonation at high altitude. I stake my career on it working safely." "That's exactly what you've done," Pierce replies grimly. "If this modification fails and kills a pilot, you'll face murder charges along with the court-martial. But if it works, you might have just won the war." He turns to Hartwell. "Squadron Leader, I'm authorizing extended testing under your supervision. 3 more flights with complete fuel consumption monitoring and engine performance analysis. If the results remain consistent, I'll forward this to Group Headquarters with my recommendation." Word spreads through RAF Hornchurch with the speed of hangar gossip amplified by wartime desperation. By evening mess, every pilot knows about Davies' carburetor modification and Hartwell's extended range flight. Opinions divide sharply along predictable lines. Veteran pilots who've lost friends to fuel starvation gather around Davies, firing technical questions about installation procedures, operational limitations, and performance characteristics. But the engineering staff and senior maintenance officers react with alarm bordering on panic. Flight Lieutenant Morrison, the station's chief engineering officer, convenes an emergency meeting on March 25th with 16 officers in attendance. The tone is hostile from the opening statement. "Gentlemen," Morrison begins, "we have a discipline crisis that threatens operational safety. An enlisted man has performed unauthorized modifications using salvaged components and improvised procedures. This sets a catastrophic precedent. If every mechanic decides to redesign aircraft systems based on personal theories, we'll have experimental failures killing pilots across Fighter Command." Squadron Leader Hartwell stands immediately. "With respect, sir, that's intellectually dishonest. Davies didn't experiment randomly. He identified a specific inefficiency in factory carburetor settings and corrected it using proven engineering principles. The fuel consumption improvement is measurable and repeatable." Morrison's face reddens. "Squadron Leader, we have established procedures for equipment modifications that exist for excellent reasons. These modifications require engineering analysis, laboratory testing, statistical validation across multiple aircraft types. One successful flight doesn't constitute proof of concept. Then, test it properly, Hartwell fires back. Put Davies' modification on 6 aircraft. Monitor fuel consumption, engine performance, and operational reliability over 50 flights. If it fails, court-martial him. If it succeeds, implement it fleet-wide, and recognize that enlisted expertise sometimes surpasses officer assumptions. The argument escalates rapidly. Morrison cites safety regulations, proper channels, and the dangers of field modifications that bypass established testing protocols. Combat pilots counter with casualty statistics, operational limitations, and the strategic imperative of extending fighter range. Someone mentions the American P-51 Mustang's superior range capabilities. Someone else suggests that British engineering pride is preventing adoption of practical solutions. Group Captain Williamson, the station commander, lets the debate continue for 30 minutes before calling for silence. A veteran of the Great War who earned his wings in 1917, Williamson understands both the importance of military discipline and the necessity of tactical innovation. His decision will determine whether Davies faces punishment or recognition. Gentlemen, Williamson says quietly, I've listened to arguments from both perspectives. Engineering concerns about unauthorized modifications are valid and important, but operational requirements during wartime sometimes demand extraordinary measures. He looks directly at Morrison. Chief, how long would formal approval take for carburetor modifications of this scope? Morrison shifts uncomfortably. Sir, proper testing protocols require minimum 6 months. Laboratory analysis of mixture control modifications, endurance testing across multiple engine variants, statistical validation of fuel consumption improvements, formal approval through ministry channels. 6 months, Williamson repeats slowly, during which time we lose approximately 400 fighters to fuel starvation based on current attrition rates. He turns to Davies. Corporal, how many aircraft could you modify using your current procedures? Davies calculates quickly. Sir, with proper materials and 2 assistants, I could modify 12 aircraft per week. The carburetor work requires precision but uses standard components. Installation takes approximately 6 hours per aircraft with proper tools. Williamson nods thoughtfully. 12 per week versus 6 months of testing. The mathematics are compelling even without considering the strategic implications. He makes his decision with the authority of a commander who has watched too many talented pilots die from preventable causes. Corporal Davies, you'll modify 24 aircraft over the next 2 weeks under Chief Morrison's direct supervision. Every modification will be documented with precise specifications and installation procedures. Engine performance monitoring will track fuel consumption, power output, and operational reliability across 100 flight hours. If any aircraft experiences engine failure attributable to your modifications, you'll face immediate court-martial. If the modifications prove successful, I'll recommend you for promotion and forward your procedures to Fighter Command Headquarters. Morrison objects strenuously. Sir, this bypasses established safety protocols. We're essentially conducting experimental testing on operational aircraft with untrained personnel. The risks are enormous. The risks of doing nothing are larger, Williamson replies firmly. Every day we delay implementation costs us operational capability we can't afford to lose. Corporal Davies has demonstrated that his modification works under combat conditions. Now we determine whether it scales to squadron-level operations. Davies spends the next 2 weeks in a modified maintenance schedule that resembles an intensive manufacturing operation. Working 18-hour days with Corporals Walsh and Knox, he transforms the squadron's fuel consumption characteristics 1 aircraft at a time. The work requires absolute precision because there are no second chances. Every carburetor modification must be perfect, every calibration exact, every installation flawless. The process reveals the sophisticated understanding Davies has developed through 3 years of maintaining combat aircraft. He doesn't simply follow rote procedures, but adapts each modification to individual aircraft characteristics. Engine 1, 2, 3, 4 runs slightly rich at altitude and requires different metering jet specifications than engine 5, 6, 7, 8, which tends toward lean mixtures during climb. Davies compensates for these variations instinctively, creating custom calibrations that optimize performance for specific aircraft. More importantly, he develops standardized installation procedures that allow other mechanics to replicate his work. The modification manual he writes by hand during evening hours provides step-by-step instructions that eliminate guesswork and prevent installation errors. Technical drawings sketched with mechanical precision show exact component positions, calibration settings, and performance specifications that turn his individual insight into reproducible technology. The first comprehensive test comes on April 7, 1943, when 12 modified Spitfires escort a formation of American B-17 flying fortresses on a deep penetration mission over occupied France. The target lies 280 miles from base, well beyond the normal operational radius of British fighters. Under factory carburetor settings, the mission would be impossible. Fighters would exhaust their fuel before reaching the target area, leaving bombers unprotected over the most heavily defended airspace in Europe. Squadron Leader Hartwell leads the formation, his modified Spitfire running smooth and efficient at cruise power settings that would have been impossible with standard equipment. The fuel consumption figures validate Davies's calculations perfectly. Transit to target consumes 34 gallons instead of the predicted 48, providing an additional 14 gallons for combat operations and return flight, the difference between mission success and catastrophic failure. The engagement over Saint-Omer proves the modification's combat effectiveness decisively. Luftwaffe fighters intercept the bomber formation with their usual tactics, expecting British escorts to withdraw when fuel limitations force them home. Instead, Hartwell's pilots engage at full military power, knowing they possess sufficient reserves to sustain combat operations and still reach friendly territory. The psychological impact on German pilots is immediate and devastating. For 2 years, Luftwaffe tactics have exploited British fuel limitations ruthlessly. German pilots have learned to avoid extended engagements, knowing that patient harassment will eventually force British fighters to disengage when their fuel runs low. Now, British fighters remain in combat far longer than German intelligence considers possible, pressing attacks with apparent disregard for fuel consumption. Flight Lieutenant David Thompson shoots down 2 Focke-Wulf 190s during a prolonged engagement that consumes 18 gallons at military power settings. Under standard carburetor configuration, he would have exhausted his fuel reserves and been forced to disengage after the first kill. Instead, he maintains combat effectiveness throughout the engagement and returns to base with 12 gallons remaining, enough fuel for defensive maneuvering if intercepted during the return flight. The mission results electrify Fighter Command headquarters. 12 modified Spitfires escort bombers to targets previously beyond their operational reach, engage enemy fighters for extended periods, and return without fuel-related losses. Operational range has increased by 68% while maintaining full combat capability. The strategic implications transform Britain's entire approach to fighter operations. Air Vice Marshal Trafford Lee Mallory receives the mission reports at Fighter Command headquarters and immediately requests detailed technical specifications for Davies's modifications. The potential for long-range escort missions, deep penetration sweeps, and extended combat air patrols represents exactly the operational flexibility that British strategic doctrine requires. For the first time since 1940, British fighters can operate with the range and endurance necessary to challenge German air superiority over occupied Europe. But the modification's success creates unexpected political complications within the Royal Air Force's bureaucratic structure. Davies's field innovation bypasses the established research and development hierarchy that employs hundreds of qualified engineers working on official fuel efficiency programs. The Ministry of Aircraft Production has invested substantial resources in developing advanced carburetor designs that promise similar performance improvements through formal engineering channels. Dr. Harold Roxby Cox, Director of Scientific Research at the Ministry, reviews Davies's specifications with barely concealed irritation. The modification achieves results that official programs have pursued for months using nothing more than standard components and field improvisation. From an engineering perspective, the solution is elegant and effective. From a bureaucratic perspective, it represents an embarrassing demonstration that practical mechanics sometimes understand aircraft systems better than theoretical engineers. Cox's report to Minister Duncan Sandys reflects this professional discomfort. While the enlisted man's modifications appear effective under limited testing, proper engineering validation requires comprehensive analysis that cannot be completed in field conditions. Premature implementation of unauthorized modifications risks catastrophic failures that could compromise Fighter Command's operational effectiveness at a critical juncture of the war. The report reaches Prime Minister Churchill's desk on April 15th, along with Fighter Command's operational assessment of Davies' modifications. Churchill, who has repeatedly demanded solutions to British aviation's range limitations, cuts through bureaucratic objections with characteristic directness. His response, scrawled across the bottom of Cox's report in red ink, reads simply, "If it works, use it. If it doesn't work, fix it. If it can't be fixed, replace it with something that does work." The Prime Ministerial directive ends bureaucratic resistance immediately. On April 18th, Fighter Command issues Technical Order 2847B, authorizing immediate implementation of Davies's carburetor modifications across all operational squadrons. The order specifically commends Corporal Davies for innovative engineering that enhances operational capability and directs that his procedures be adopted as standard maintenance practice throughout the Royal Air Force. Implementation proceeds with wartime urgency across Fighter Command's operational structure. Maintenance crews receive intensive training in Davies' modification procedures, working from his handwritten manual and detailed technical drawings. The process resembles a crash manufacturing program that transforms British fighter capabilities within weeks rather than months of traditional development timelines. By May 1, 1943, over 400 Spitfires and Hurricanes carry Davies modifications. Fuel consumption drops consistently across all aircraft types, with average range improvements of 65% at cruise power settings. More importantly, combat effectiveness remains unchanged while operational flexibility increases dramatically. British fighters can now escort bombers deep into German territory, conduct extended patrol missions, and engage in prolonged combat operations that were previously impossible. The tactical implications revolutionize fighter command's strategic doctrine. Long-range escort missions become routine rather than exceptional. Deep penetration sweeps over occupied Europe disrupt German air operations and force defensive reallocations that reduce pressure on other fronts. British fighters appear over targets that German intelligence considers beyond their operational reach, creating uncertainty and forcing tactical adjustments throughout the Luftwaffe's defensive structure. The psychological warfare aspect proves equally significant. German pilots who have grown comfortable exploiting British fuel limitations suddenly face opponents with unprecedented endurance. Luftwaffe tactical reports from June 1943 describe British fighters maintaining combat effectiveness far beyond previous parameters. Squadron commanders note increasing reluctance among German pilots to engage British formations, knowing that fuel constraints no longer guarantee easy disengagement opportunities. Davies receives promotion to flight sergeant on May 15, 1943, during a ceremony attended by Group Captain Williamson and visiting dignitaries from Fighter Command headquarters. The commendation specifically recognizes innovative engineering that enhanced operational capabilities under combat conditions. But Davies remains characteristically modest about his achievement, deflecting praise to the pilots who validated his work under the most demanding circumstances imaginable. The modification's success spawns similar innovations throughout Fighter Command's maintenance structure. Mechanics across different squadrons begin examining their own aircraft systems with renewed confidence, identifying inefficiencies that escaped official engineering attention. Flight Sergeant Davies becomes an unofficial consultant, reviewing proposed modifications and providing guidance on implementation procedures that avoid the bureaucratic obstacles that nearly destroyed his own innovation. Technical Sergeant Robert MacLeod at RAF Tangmere develops complementary fuel system improvements that reduce fuel consumption during climb operations by optimizing mixture settings for varying manifold pressures. His modifications, directly inspired by Davies's success, extend range by an additional 12% when combined with the original carburetor improvements. The synergistic effect creates operational capabilities that approach those of American long-range fighters. By war's end, Davies's impossible modification had been implemented across every British fighter squadron in Europe. His handwritten manual became required reading at RAF maintenance schools. The corporal who dropped out at 14 had rewritten the textbooks written by university graduates. Sometimes the greatest innovations don't come from the experts who know why something can't be done, but from the mechanics who refuse to accept that it can't be done.